Good afternoon. Welcome, distinguished guests, faculty, and friends to this very special event, the second annual Ernest S. Koo Distinguished Lecture. Each year, the Koo Lecture brings an outstanding leader in technology and engineering to our campus. Last year, we launched the series with a talk by Intel co-founder Andy Grove. Today, we are honored to continue building this tradition of excellence with our 2013 Koo lecturer, Bill Sullivan. We are delighted to be presenting today's lecture during Engineers Week, which has been a continuous tradition on the Berkeley campus since 1951. It's a completely student-run event and a completely student-sponsored event, and this week has been packed with activities that highlight engineering and provide exciting opportunities for students. For example, on Monday, Stephen D. Bechtel Jr. joined us on campus to celebrate the reimagining and renovation of the Bechtel Engineering Center, our hub of student activities and services. And today, we've announced a new program to provide research and design experiences for undergraduates. Those of you that were here early, you might have seen me going around catching every unsuspecting undergraduate there to show them this program. It is a program funded by the Qualcomm Foundation called QUEST, Qualcomm Undergraduate Experiences in Science and Technology. It's paid research experiences for our undergraduates. We want to get our undergraduates starting to do research, design experiences early and often. And I was going around especially looking for freshmen to get them to join into this program. Quite a few takers, by the way. My advice to the students here today, please check out the poster in the lobby outside and be the first to apply. Today, a true highlight of eWeek, Berkeley engineers have a chance to hear from Bill Sullivan, one of the leading figures in Silicon Valley today. This year's student co-sponsor for the Koo lecture is the Berkeley chapter of Eta Kappa Nu, and those are the folks there in the back who are welcoming you, and the Electrical Engineering and Computer Science Honor Society. Our thanks go to HKN for its great work in helping with this event. Thank you, HKN. And this wonderful lecture series was endowed through the generosity of Ernie and Bettine Koo, who are with us today. Ernie was Dean of the College of Engineering from 1973 to 1980, and he has been a national leader in engineering education throughout his career. He is Professor Emeritus of EECS and a true trailblazer in the design of integrated circuits and systems. It's my pleasure to invite Ernie to say a few words. By the way, one word about Ernie. You know, Ernie is back on his feet and is talking to us not quite a week after he had major back surgery. So it's really wonderful that you're here. And Ernie will deliver a few remarks, and we've had it set up so Ernie can deliver his remarks from the front row here. Thank you, Ernie.
Yeah. This is my special chair. Greetings to all of you. Can you hear me?
Yeah.
Thank you for coming today. I came to U.S. in 1948 from China by slow boat, 3 weeks. That was after I took a year and a half courses in Chiao Tung University in Shanghai. Some of you may know that place. I say the best in China. After I came to the States, I went to University of Michigan at Ann Arbor, to MIT, and to Stanford, and finally finished my PhD degree. After 4 years at Bell Laboratories, which no longer exists here in the U.S., I came to Cal in 1956. I'm proud and grateful to have had a long and satisfying career here. My wife, Bettine, here, and I endow the Distinguished Lecture Program to shine a light on the outstanding contribution of technology leaders in our society and bring to the best among them to College of Engineering at Berkeley. We wanted the annual lecture to be the highlight of the academic year for students and friends of Berkeley Engineering. I'm happy that the vision for the lecture is now reality. Many thanks to Bill Sullivan for presenting today's lecture, and to all of you for being with us for the very special annual event. Thank you. Thanks.
It's an honor to be Ernie's Berkeley colleague, and I thank him and Bettine for making this splendid occasion possible. As the Dean of Engineering here, it's been my privilege to meet many remarkable people and business leaders from around the world. Few can rival Bill Sullivan's vision and skill as the CEO of Agilent Technologies. Agilent is the world's leading measurement company, creating equipment and solutions for chemical analysis, life sciences, diagnostics and genomics, and electronic measurement. Bill took the helm of Agilent in 2005, and he knew the company from every angle. He joined Hewlett-Packard in 1976. He became an HP leader of divisions focused on optical communications, communication semiconductors, and components. In 1999, when Agilent was spun off from HP, he was named to the top position in the Semiconductor Products Group. He was Agilent's Executive Vice President and Chief Operating Officer before becoming CEO 8 years ago. Bill is a graduate of UC Davis, and he knows and loves the University of California. He has been a staunch and eloquent advocate of education and of public higher education in particular. And he has been a great friend of the University of California in many, many forums in Sacramento and in many other places. At Berkeley, he serves on our College of Engineering Advisory Board, and we are very, very proud to call Bill a very good friend. Agilent has been at the forefront in recognizing the potential of biology to be the catalyst of the next remarkable leaps in technology and science. Bill and the company have been early and strong supporters of Berkeley's Synthetic Biology Institute, the leadership of which is right here in the front row, as an example of their great vision for the role that engineering can play in the century of biology. To share his far-reaching ideas, I'm really delighted to welcome Bill Sullivan.
Thank you, Dean. Thank you, Ernie, for coming and having such an honor for myself to be able to speak at this event. Speaking about the century of biology, it really is going to be an incredible transformation. And I remember when we started this journey at Agilent, all the engineers were saying, what's going to happen to me? Hopefully over the next 30 minutes, I will convince you that the story of the century of biology will in fact be built on the core engineering that will come out of institutions such as this. I'm going to tell this story as HP and Agilent is that basis. Not so much as a plug for Agilent, I'll take that anyway. But it really is a story of one of the founders of Silicon Valley, a company that was started by two graduates from Stanford that built an engineering powerhouse. I'm also going to talk about innovation and what I call the cloud of innovation of how the disciplines of engineering, chemistry, biology is coming together to be able to drive what I do believe is the century of biology that we live in today. And finally, it really is a lot of story about me. The dean talked about my background. Actually, when I graduated from the University of California at Davis, I wanted to save the world. I wanted to be an environmentalist. Back in the 60s, global warming was well understood, and it quickly dawned on me that the world didn't want to be saved. It's not clear to me the world wants to be saved yet today, But I was fortunate, hired on at Hewlett-Packard, went back to school and took 2 years of electronics and understanding circuit design and amplifiers and all that, and did 2 years of that. Actually spent a year. Somebody sent me to Stanford for a while, too. And so it really has been a transformation for myself when we separated from Hewlett-Packard to be head of all of HP's chip development, today to talk about Agilent, which is quickly becoming a biology company. Many of you of the faculty know the history of Hewlett-Packard. Unfortunately, and I'm quite biased for many of the students in this room, not so sure that people understand the history of Hewlett-Packard. Hewlett-Packard actually started as a measurement company in 1939. And in fact, when I started in the company in 1976, we had just started getting into the computer business. The computer business was a device that was going to help drive measurement instruments for the company moving forward. Today, of course, Hewlett-Packard, that many of you know, is a $130 billion colossus, and Agilent, starting in 2005, when I became CEO, essentially focused 100% on measurement science. Using our core electronic measurement capability in 1939, we have slowly built our capability into chemistry, into life science, and now into diagnostics. Hewlett-Packard themselves made the first decision almost 50 years ago to move into chemical analysis. That they said, hey, if I'm measuring photons and electrons, why can't I in fact measure chemical molecules? And that's how that started moving forward. Today, Agilent Technologies, and many of us may not know this, that we are an S&P 500 company, one of the largest 500 companies in the United States, even though much smaller than Hewlett-Packard. We are actually classified in the healthcare sector today. And if you go into Yahoo or something like that, it says we're an IT company, but the reality is 2 years ago, because of the transformation I'm going to talk about, again, our focus on the century of biology, Agilent Technologies today is considered a healthcare company. If you look at Agilent, we really provide measurement solutions in four areas. The electronic measurement, of course, the college here knows that very, very well. I was very lucky to be shown the lab that we're very, very happy to be able to make a donation, to be able to provide equipment for students to learn the basics of electronics, to be able to apply that to projects, to be able to apply it to future needs as you as a student go out into industry moving forward. In chemical analysis, the things that you see every day, is the food that you ate safe? Is the fish that you just ate is really fish? I don't know how many of you saw that in the newspaper. Something like 80% of the tuna that you eat in sushi, in fact, are knockoffs. In fact, not even what you think you're eating. And so again, all the people who take drugs to enhance their sports has been just a great opportunity for Agilent. I often joke the more cheaters there are in the world, the better business is for Agilent. In 2005, we moved into life science. Life science, for many of you, and many in this room are very, very young, and so at most you take is an aspirin. But we want to make sure the ingredients in that aspirin are absolutely the correct ones, and it dissolves in your body at the proper rate. Other people in this room are even more excited about life science, dealing with disease, extending the quality of life. And so for myself, particularly where I am in my career, I am particularly excited about the advances that one is seeing in life science. And ultimately in diagnosis, how do you improve the human condition? How do you deal with cancer? How do you deal with heart disease? And Agilent, again, wants to be a foundation and be able to bring those measurement tools together. So if you look at this sheet, and you looked at it back in 1976, all you would really see would be electronic measurement. And today, Agilent, all those years later, the electronic core is 1/4 of this picture, to give you some idea of the transformation that has gone on. Just give you an idea of what we make. All of you in the engineering school, particularly in the electronic side, know what oscilloscope is, network analyzer, spectrum analyzer, and signal analyzer, the core workhorse instruments for essentially any type of design, verification, and manufacturing. But down below are the instruments that are used in the analytical instrumentation space. In a moment, I'll show you how similar many of this is, but the instrument's quite different, and outside of many of you that are in the chemical engineering school are not familiar with some of these instruments. But you can see there's just literally a dozen instruments that basically build this foundation for measurement. So when you look at measurement, and I tell this to all the analysts in New York all the time, measurement science is pretty arcane, but yet I would argue without measurement science, it would be very, very hard to have very much discovery. The first measurement tool was discovered in Mesopotamia, 3000 BC. So I remind every investor in the world that there are not that many instruments that have been, or businesses or markets that have been around for 5,000 years. Agriculture, but there is. And, you have companies in Silicon Valley that come and go, and all of us know all those names, but we've been around since 1939. And our simple job is to work with every engineer, scientist, researcher in the world to take this sample, doesn't matter, as I said, a photon, electron, a molecule, some biologics, to be able to detect it, acquire that information, analyze it, obviously integrate it. And the biggest part is how do you help somebody interpret what they see for discovery and invention. That is what we have done since 1939. That was the vision of Hewlett-Packard, and I feel very, very proud and honored to, in fact, be the latest CEO in a long tradition of being able to provide the best possible environment to make that happen. And I think the beauty, and I think that this is something that the university here, the University of California, has done, has been able to continually to identify the mega trends of innovation that we face. Obviously, as I said, when Hewlett-Packard came out of Stanford in 1939, it was all about electronics. It was all about the back then in tubes, the invention of the transistor, invention in wireless, dramatic revolution as going forward. Many of the people in the first instrument that was made by Hewlett-Packard, an oscillator, and many people associate that with Disney and Fantasia, which was the first automated cartoon. Again, many of you in this room have never seen that cartoon. But I can remember as a child seeing that and just, wow, how can somebody do that? That oscillator was actually used to balance the sound system into what were at that time state-of-the-art movies in terms of how sound was projection. How far have we come over that period of time? And over the course since 1940, there have been dramatic changes in technology and the spread of technology moving forward. And I will put in my second theme that I have is that the university system in the United States, the University of California, has been one of the biggest differentiators in this country that has led to the innovation, the number of inventions, and the growth of this country. Many of you, and you can see other talks that I have given, say that in fact, if this country systematically destroys the underlying public education system, particularly epitomized in the University of California, this country will not have the competitive advantages that we have versus other countries. I have the privilege of visiting every top university in the world, and these universities are good, the students are good, but there's a magic in the competition between Berkeley, competition with Stanford, the University of California, San Francisco, Silicon Valley, San Francisco. It has created the technology capital of the world. And even in an environment when people say of high taxes and all the rest, look at what we together have been able to do. And here today, and how privileged we are to be able to help support the synthetic biology effort here at Berkeley, the whole movement into personalized medicine that is going along in the South Bay, life science, communications, and that doesn't even count all the social networking that is going on. Our ability to be able to drive, to be able to capitalize that has been the secret sauce, and we should do everything to ensure that we can continue to make that happen. To give you some idea in terms of how quickly this has changed into biology, this is the size of the measurement market today. It's roughly a $54 billion market, peanuts in the total $75 trillion world economy. But that's basically what scientists and engineers use to be able to do their invention. And on the bottom, the classic electronic markets of communication, aerospace and defense, and in electronics, about $13 billion in measurement. To give you some idea, that market in the world economy is only about 6% of the world's GDP. This is not to scare any of the engineers and future engineers, because it's a huge $75 trillion economy. But just look at food, energy, chemical markets. The measurement tools just to support that industry are equal to electronics. And just look at the pharma industry, the academic and research part of life science and diagnostics. And this diagnostics is only the molecular diagnostics. This isn't even counting, the standard type of diagnostics that you have today. And you can just see the dramatic shift into where the opportunities rise moving forward. And you can see the shift inside of Agilent. In 2005, only 17% of the company in Agilent was not electronics-based. Today, 52%. At the end of this year, it's going to be, in fact, 55% as we move forward. But if there's any message I would leave for all the hardcore engineers in this room, is that if you go in and look at all the the bachelors, the masters, and the PhDs inside of Agilent, and the 3,000 researchers that we have, 60% of all those people that are researchers in the bioanalytic all have engineering degrees. So that's good news, right? Why is that? So this is a very, very complicated slide since 1939. And this is what I define as this cloud of innovation. And I've spent a lot of time, and many of you may know, I was in research and development at Hewlett-Packard for 10 years. And I've spent a lot of time thinking about how does innovation really work. And the reality is, and the data, and it was an interesting study that was done by HP decades ago, is that the major differentiation in innovation is that the right people were identified to work together to be able to see something in the future that the conventional wisdom wouldn't have. And oftentimes people talk about looking around a corner. Obviously you can't do that, but there are just some people that are able to make that happen. A lot of them, of course, live here on Berkeley, and given the enormous amount of contribution that is made. But how do companies create an environment that that individual that sees the world differently is in fact get a share of mind of somebody? I'll never forget, as an individual, Gary Gordon, who came to me, and it was in the labs, and there was another individual named Jason Hartlove, and I was at that time managing an RF microwave opto group, and they came to me with the idea of the optical mouse. And many of you, if you asked who invented the optical mouse, you'd say Xerox PARC and all the rest. It was actually Agilent, HP Agilent. And they wanted to be able to commercialize this optical mouse. How simple. They went to the computer guys. Oh, trackball mouse is fine. Trackball mouse is fine. Why do you need an optical mouse? Why does the world need that? And so this is the beauty of HP in terms of innovation. Does anyone remember who introduced the world's first optical mouse? Bill Gates. Bill Gates did. Bill Gates was standing on a stage like this with a mock-up of that optical mouse this big. I ran into Bill Gates at a fundraiser, and he still remembers it. This guy's really smart, actually. It's no surprising how rich it is. And he's sitting there. So in that case, HP didn't have the desire to do it because nobody could see around it. And instead of selling at that time was $2.50 optical mouse, Microsoft sold the world's first optical mouse for $75. Today, the world's 100% optical mouse, right? So what we did here, and again, Darlene Solomon, which many of you know that, wrote down some of the biggest cross-organizational inventions we ever made. So we made the electronics measurement the biggest since 1939. We have life science and chemical analysis. And of course, we regulated the $130 billion company of HP down to this little pie over here. But it's important, all right? So I just want to make sure where the bias is coming from, all right? So let me just give you one example. And so you look at this, and what that box basically says is a mass spectrometer time of flight. And I'm not going to go through that. So what in the world is a time of flight mass spectrometer? Well, that's what it looks like. And for all of you that are biologists, you're going to hate my explanation. But basically what this instrument does is you take an element, a molecule, you ionize it, you send it down a vacuum, and of course all the molecules or ions are going to start to separate. And they're going to separate as they go up this big tube and back down that tube, and they will bounce against a photomultiplier tube, and you will be able to calculate the mass of that instrument. And so pretty straightforward. At the end of the day, everything in the day is pretty basic engineering physics to be able to make that happen. And so when we entered this market into mass spectrometry and said, okay, God, what could we learn? Well, all of you in this school on the engineering side have used an oscilloscope, right? Oscilloscopes is the common workhorse in the electronics industry in terms of time domain. We have lots of instrument frequency domain, but on time domain. And so somebody figured out and said, if I go and I take that chip inside of an oscilloscope, that is able to make billions of samples per second, and all of a sudden I put it in terms of the analog to digital conversion inside of this mass spectrometer, I can get a higher sample rate. So this up above is it's a sample of a water, it's a contaminant. And again, that contaminant potentially can cause cancer. There are 4 elements that chemical compositions, and the existing time-of-flight instrument can't tell what's in there. You substitute the parts from the oscilloscope, and guess what? You can clearly identify exactly what that compound is. So here's a simple example of creating an environment of how do you, in fact, leverage this core technology into a completely different world in terms of mass spectroscopy. Another one, RNA, DNA. What in the world is HP at the time or Agilent getting into DNA microarrays? And how in the world would you do that? What would you do? Well, it turns out that somebody figured out that we put down ink pretty well. Inkjet printers. All of you know what an HP inkjet printer is. And so somebody says, well, if I'm squirting a bunch of black ink, red ink, yellow ink, blue ink, why can't I squirt down some synthetic DNA? Not a bad idea. I'm not sure who in the world thought that. That's why they'll never let me in a lab again. And so what they came up with, and again, the MERS are basically the length of the bases on the end, inside in the DNA strand, we can write down up to 1 million spots of synthetic or DNA. We can do RNA as well, and basically it's used for gene expression. Wow, how do you create that environment to be able to make that happen? And then somebody says in engineering, not only can you do that, well, I'm looking at all these genes, and if I can make synthetic RNA, one of the biggest issues that, of course, we have is childhood defects. How, in fact, do I do the evaluation of the chromosome? How do, in fact, do I look for deletions? It's called a race AGH. It's a hybridization process. And next thing you know, you have a whole new market in terms of evaluating chromosomes and the probability of genetic diseases. Obviously, huge ethical, political issues that society has to deal with, but the ability to identify in a fetus inside of in vitro fertilization what types of defects are there is just become an enormous tool to understand diseases and trying to figure out what do you do to be able to stop these terribly debilitating diseases that many children are born with. And so all of that started, all of those ideas came from somebody deciding that they're going to print out a piece of paper, where many of you in this room, in fact, when even thinking out printing out a piece of paper, because you'll look at everything on your iPhone or moving forward. So let me stop for a moment and talk about this. And I think when I looked at this chart, I don't know, Dean, if you have things that are actually similar to this, say, well, geez, does this sort of look like a school? But what we tried to do, and so you took our core engineering, electrical, chemical engineering, biologics, mechanical, all of our software disciplines, all of our core sciences and physics and optics and math and so forth, and we had to build a layer of molecular biology, cellular biology, computation, and microbiology. And that is what we have been doing over the last 8 to 10 years, is to be able to create this environment, this ecosystem, so that, in fact, we can get these disciplines together to work together to be able to participate in this web of innovation, this web of ideas, the web of ideas that I had talked about moving forward. Very, very similar to what, in fact, you do as a basic principle, as well as education and research. How do you, in fact, do that? Our job, of course, is to create that environment, commercialize it to drive a profit and to benefit for our customers and our employees moving forward. So what we've done to be able to do that is obviously the endless search for talent to be able to make this happen. Obviously from the experience pool, but from all of the top universities in the country. And we're very, very proud. And this will be my plug. Need a job, come see us, at least consider us moving forward. The second thing, though, and this is really directed for a lot of the students as you go out into the workforce, we do a management assessment because all of the managers, look at my background. I was going to be an environmentalist. Went to school, and now I'm trying to fake it to be a biologist as CEO to make sure the investment's going right. We spent $700 million in R&D. and how do you decide where that money is going to go, is that we assess the talent on not only knowing your domain knowledge, but to be able to work across these disciplines to help drive teams forward. I gave you a couple of examples in terms of how teams got together. If you were the manager of that team, would you have thought to go talk to the oscilloscope people to be able to drive electronics that would improve your sensitivity in measuring water? Wow. Not obvious. Not obvious. And quite honestly, a lot of disciplines are so narrow, very, very hard to be able to integrate across a wide spectrum of environment. And so we actually do a talent assessment to, in fact, do that. And we're always looking for the individuals that have that ability to do that, because it is incredibly rare that individuals can have the breadth of know enough to, in fact, integrate and then build teams to be able to get that happen. The other is the learning environment. To put a plug in for UC San Diego, they have a big program for all the people who are engineers, and you try to turn them into biologists. So we send everybody there. In addition to that, last week, or I guess the week before last, we had the Agilent Technology Conference. And what we did is I wish we could bring all 3,000 researchers together in San Francisco, but we brought roughly 850 researchers together. And again, this is the beauty of the institution that you have here. You can bring people together, these cross-disciplines, and you create an environment for them to share ideas. They set up a whole social networking way to be able to, for having these 850 people to be able to communicate and share ideas and post ideas so that people could see them. And quite honestly, I'm not the greatest tweeter. In fact, I don't know how to do that. I know how to text, but I don't know how to tweet. But they created a whole nother environment for them to be able to do that. And we've been doing this every 2 years. We actually track the ideas that come out of that conference that in fact get commercialized moving forward. And then finally, it's all built on the core values of Hewlett-Packard in terms of absolute respect for the individual and a culture of collaboration to ensure that we can get the best ideas moving forward. So I'm going to close with just a couple neat things that we're doing. And again, these are things that I think are just really fun, that, again, to reinforce the need for hardcore engineering, and secondly, to be able to bring the engineering excellence, electronic excellence, the chemical excellence, and the biologics together for ideas. This is a scanning microscope. And basically, you can see these are bacteria that scan. Basically, you can get down very, very low resolution, basically using a probe and a laser to be able to do the topology of your specimen moving forward. Well, our big microwave group is up in Santa Rosa. And so they've heard me talk about the century of biology. Everybody up in Santa Rosa, again, we have thousands of people up in Santa Rosa, hardcore RF, microwave, digital folks up there. And they're going, well, Bill's talking about biology. Geez, is there any way that we can apply this technology to something else? Because we better do that really well, because they're going to be expecting this. So I'm not sure who thought of it up in Santa Rosa, but why don't we take a microwave signal and jam it down this probe, and what do you get? Well, next thing you know, that you can see the impedance, and you can see the capacitance. You can see all kinds of features that are down in the molecular level. And in fact, the first one, I was down and I was looking at it, and myself being an old semiconductor guy, and they're showing the topology at the top of the circuits, and you're going, wow, that's really interesting, and everybody has seen a sim picture at least of what that looks like. And they said, Bill, watch this. They imaged the doping implant under every base on every transistor in that wafer. And I'm going, wow. Because back in the days when I was in semiconductor, the whole doping profiles and all the rest were so hard to sort out, and you had to infer what it was. They could actually see it. And they actually showed me where there was a defect in the reticle, and there was no implant. There was no implant at all. And you could physically see that. Somebody had enough sense to figure out how that said, I'm going to take this microwave, and that's one of our network analyzers, and in fact put that down that probe. Here's another one. This is with Dune Medical. Unfortunately, cancer, again, there's about 5 diseases will kill 80% of us in this room. And cancer is one of the leading one. And again, breast cancer, a terrible disease, as you all know, for women. And the big issue, of course, is in lumpectomy, are you getting all the tissue or not? And another example of X-ray, in fact, is not very good. All kinds of problems. Enormous amount of effort is going in on using microwave. Turns out microwave is far better in terms, in fact, understanding the borders of where the cancer is to ensure that there is removal. And as you know, between a mastectomy and a lobectomy, there's not a lot of statistical difference between the two. So how, in fact, do you make that change? Another example of taking hardcore microwave technology and applying it to a completely different field and a different application versus the conventional wisdom, and in fact has made an enormous, I believe, a potential enormous contribution. And again, this was just recently approved by the FDA. Digital pathology, all of you know about visualization. And so this whole idea of, again, cancer, and again, between our central research labs, again, we made a recent acquisition of DACO, but this whole area, which was a leader in pathology, is really understanding the type of cancer you have to be able to get the right treatment. I don't know how many of you have read in the Wall Street Journal, I don't know if it's accurate or not, but 50% of cancer diagnoses are not done correctly. Get the wrong medicine for the wrong type of cancer that you have. And again, while we made some progress against cancer, we have not made, as much versus the return in terms of what we're spending. So there's a huge effort not only to try to improve the analysis of the genetic area, but again to be able to get those, to be able to computerize those devices, and to be able to dramatically improve the analysis of that. Many of you may not know this, but if you ever think you have a tumor that may be cancerous, they take a sample, they slice it, they put in paraffin, stain it, look underneath the microscope, and make a determination of your cancer. If it's yes, they do these advanced stainings to see what type of cancer it is, and then they save these samples. And they're all stored manually. Could you imagine what could happen if you could have this database of cancer and then to cross-correlate that back to the treatment moving forward? So again, enormous. And the computational issue, when people talk about big data, and I laugh sometimes. I mean, Agilent's relatively small. We actually manage the company on about 4 petabytes of data. Every time we put in one of these life science sites, the computation needs just go right through the roof. The IT people are calling me up, Bill, you know how much bandwidth these people are taking? And I'm sure here at Berkeley you know that as well, as soon as people get excited about this stuff. My last example on this is, and unfortunately this was a collaboration that we did with Harvard with George Church. One issue in synthetic biology, and that's why I've been so excited about it. Synthetic biology is already having an impact on life science, already obviously in the chemical industry moving forward. It's going to move into the food industry. The big issue is they're going to move into the computational area. And I always have lots of debates about molecular computation and where that's going when silicon runs out and all the rest. And so this was something that we did, and again, George and the Harvard team did most of the work. We basically wrote the code on the synthetic DNA. But basically, what we did is that we wrote 5 megabits of data on DNA instead of ones and zeros. I think it was the A's and C's were 1, and the other bases were 0. And again, they were able to then ship it over to England, ship it back, decode it perfectly. And literally, you get every book, every record in the world, and a bunch of white dust in the bottom of a vial that will last 10,000 years. I must admit that this will not be in your store soon whatsoever, but in fact, very, very interesting in this whole area in terms of how synthetic biology, in fact, I do think someday, I'll be long gone, but someday will in fact be a powerful tool inside of the computation computer market moving forward. So if anything, in closing, it has been incredible transformation for Agilent. I've been so proud to be involved and honored to be part of the school here and the transformation you have, the professors you have, the vision that you have to be able to reconstruct the school, not only to ensure that we have the basics and have solid people with great domain knowledge to be able to enter into the workforce and to be able to enter research, but to be able to redirect the research dollars to collaborate like companies like us. We're just one of any. TI has also made a huge investment, I'm sure focusing again on the integrated circuits. And this collaboration between Agilent, the collaboration and Berkeley, the collaboration you have with other companies, in fact, is what, as I said, made this valley. And I just couldn't be more pleased. So excited for you. You guys got a great curriculum. And just look at what has happened in a very, very short time in a company that's only an hour drive away. Thank you.
I think, Adam, this may be your cue to pull the Library of Congress out of your pocket.
Yes. Just got it, yes.
I'd like to invite people to ask a few questions to people with microphones. I'd like to give some special consideration to students. Please tell us your name, major, year in school, whatever you, something like that. Please. I actually don't see who's...
Oh, thank you.
Yeah.
Hi, I'm actually a B. student scholar from the University of Copenhagen. I was just wondering if you are entering the race of genome sequencing or if you're considering it at all. Of genome sequencing, like developing genome sequencing platforms.
Yeah. So where we are, and again, welcome. I think you must be familiar with DACO. DACO, in fact, is one of the leading companies in pathology that is headquartered right outside of Copenhagen. In sequencing, which I didn't mention in terms of on the DNA microarray, not only have we done array CGH, we've also used it for gene partitioning. And so right now, in terms of the whole sequencing, we're the leader in the partitioning of the genome going into the sequencer. So the reality is, and again, this is the big debate that's happening in the research environment, they want as long a strand as they can and want as much data as they can. It's our personal opinion that as it goes into the clinic, one will be, in fact, focusing on certain parts of the genome that will have been determined will be related to some disease or some diagnosis moving forward. So what we have today is that we're a leader in the preparation going into the reader. We have an enormous amount of bioinformatics in the analysis, but we don't have the reader. And many of you that know Darlene Solomon, every time I see her, I ask, where is our reader? And that is the big debate. As you know, two other companies are the Life and Illumina have the two biggest positions, which are mostly research type sequencers. They obviously know this is going to go into the clinic in a matter of time. There are a lot of startups, and Agilent is continuing trying to figure out what to do in that area. But we would love to have the reader part itself. And again, this goes back to the core engineering. I'm always bugging all the engineers because from my perspective, yeah, I understand DNA, and yeah, it's real small, 2 nanometers, but so what? You can see where I come from. I come from the semiconductor industry. Can't you guys figure out a way to easily measure this accurately moving forward? Because that's always one of the big issues, too, when you go to diagnostics. The reading of your genome has to be quite accurate, to say the least. But great question. So anybody's got any ideas, I'm definitely open to those.
Hi there, I'm Praneet. I'm a student of electrical engineering here. And basically my question is, what are your thoughts on the future of personalized medical devices, and especially, bringing healthcare costs down? So, for example, a device that plugs into your phone that you can check, blood measurement, things like that.
Yeah, it's a great question. So the technology today exists to have more personalized medicine, doc in the box. It's actually quite easy. I can remember years ago the labs just, taking microliters of blood and running analysis. That's all doable. Right now, and again, this is the opinion of Bill Sullivan of 1 out of 300 million people, not necessarily the CEO, but the healthcare system in the U.S., we're just at a gridlock on how to deal with the cost until there's a crisis, right? There are just too many people that have vested stakes that it's hard to move forward. My personal belief is the big breakthrough in personalized medicine will come in emerging markets, China or India, because they have more of a green field. We have met with them because they have to provide low, cost-effective healthcare to hundreds of millions of people, and they can't do it the way the West has done it. So I believe that's where you're going to see the big breakthroughs moving forward. You will continue to see incremental breakthroughs in the U.S., so don't get me wrong, we're making progress moving forward. But to really get a broad breakthrough that's statistically valid, my personal opinion, you may see it in emerging markets before you see it in the U.S. or Europe. Again, I could be wrong. Yeah.
Hi, my name is Alyssa Rosenblum. I'm a recent graduate of the doctoral program in molecular and cell biology. My question is Agilent working on any biological sensors that could be used inside the body to identify disease or bacteria or viruses, as opposed to just developing machinery to identify?
Yeah, it's a great question. Right now, our focus has been on the measurement side. In the area of, and we obviously have the capability of making very long synthetic oligos and moving forward, and so we have a big debate what to do. Right now, our focus is to try to, just like we've done on the design side, many people don't know it, but we're actually the leader designer on RF microwave chip design on the very, very high frequency, coupled with our electronic measurement. Can we be the design house on the synthetic biology side and the molecular side? And so somebody would come to us with their formula and to say, moving forward. This is third-hand information, so hopefully it's reasonably accurate. Is that the Coke bottles you have now are synthetically made with organic. The cost of developing these things is actually quite expensive. And so from our viewpoint, we'll obviously measure the measurement tools, but can we in fact help on the design to improve the probability of doing something which you would do instead of making it more by trial by error? And that's very consistent, I think, with the charter here and what the school's been trying to do as well.
Hello, I'm Ashkan Borna, postdoctoral in electrical engineering department. So I have a question for you. Can you give a comment on the two factors if the companies want to go to the bio research? Number one is the slow time to market, from the time you design the thing until you make your way to the market. And number two is that the companies usually, their target application had a huge market, for example, cellular. But on the bio, there are lots of different applications that the market actually is not that big. So could companies actually survive on developing and embarking on those paths?
Yeah, it's an interesting question. And so what's fascinating about the biology market is that if you look at it from our perspective, the vast majority of the research is done in academic university resources. That's why this whole debate on NIH funding and everything is so important moving forward. And if you go to Sandhill, again, we have the venture capital set in the world, to your point, the time to market and making money in commercialization is so wrong, it's highly regulated, that people get nervous about that type of long-term investment. And so what you're having today is you have the university systems putting an enormous amount of money in this space. Big pharma still has, in the biotech and the drug discovery, still has large R&D. And then you have some of the measurement tools, and we're little in total amount of dollars, and to be able to make that happen. And that's why, personally, I believe the future of research, particularly on the biology side, is absolutely paramount. Because I believe, and this is a role where I think government plays enormous advantage, because of the time constant commercialization, somebody has to fund that. And in the world today, when every CEO in the world is under so much pressure to say, hit your numbers in 13 weeks at the end of the quarter, it's really, really hard to be able to make these long-term investments. I'm incredibly fortunate coming from a company that has a long history to be able to make these investments, still has a central lab, but that's becoming an abnormal. And we could have a big debate about American capitalism right now, but that is a role. And I believe if you see big cutbacks in the government, you're going to slow down the progress of advancement. Again, this is an opinion of one out of 310 million people. I'm not speaking just speaking for myself on this.
Bill, you just gave a talk about why the century of biology is great for engineering. And I know we haven't rehearsed this, but we have the Dean of Biological Sciences here. And I'd love for him to respond a little bit. I know it's off the cuff. Well, he's vigorously shaking his fingers saying, no, but I'd love to put you on the spot.
I'll talk to you later, Shankar. Well, I'm not sure if this is a question or a comment, but you've been talking about how to get engineers and biologists to work together in a commercial setting. But I wonder if you have any thoughts about how to get them to work together in an academic setting. Because I think, it's from my perspective, it's proved very easy to get engineers to think about biological problems. It's more difficult to get biologists who think about discovery to become interested in engineering and practical applications. So how do you have any sort of cultural insights?
Yeah, it's a great question, and I'm going to give a joke about this. I was in Wall Street last week, and we got reclassified in the healthcare group. So a lot of them are biology backgrounds. Do you know how hard it is to tell biology? They understand cell phones, but they really don't care as long as it works. Because I think that what we've done, there's actually on the, forgetting the name, who's the big IDEO in Palo Alto, the big design house? They actually have a little seminar on how you get engineers, physicists, and biologists to get along. They actually have this, they actually have a little course that they do moving forward. And because it's such a different different approach to what's going on. The one thing that we have done, and actually UC Davis actually tries to do this across their disciplines, is to build a common language. It's amazing how different the language is. You know, and again, a lot of the PhD biologists, typically, they have physics background, so it's not like they don't know about it, but trying to build a common language together moving forward. And the second thing we've done, which is a big issue with the labs, which I think we've done a very good job, the issue of collaboration driven on an end goal. And I think that's for academic, where the principal investigator kind of dictates where the direction is. The advantage that we have is that we can set certain objectives and let these guys going. But the common language has been very, very helpful for us. And so when we got this 850 scientists and engineers together in San Francisco, the first part of the day was just purely tutorial to try to get a common language together so that people could understand exactly what they're saying, because I think that was part of it. So that's it. But it's a difficult issue, and IDEO actually is quite humorous how they've addressed this problem. I'm dating myself a little bit, but there's a bunch of HP, some of the HP people had left and started that company.
We'll
but it's quite interesting.
A very good lead to follow up with the
IDEO folks, that's very good.
Steve, we should follow up on that.
No, yes.
You talk about the early days of DNA computing. And so, there's a stalwart in our faculty who used to do DNA computing at Princeton. So here's Lydia Zone. This is professor now of mechanical engineering.
I'm going to be in big trouble.
So what is your sense from your early days of working on DNA computing, and what's the title of this?
I'm working on cancer now.
You mean no DNA Pentium soon?
I'm doing high-seq mRNA analysis off of CTC. So, yeah.
I was in Yale, and this molecular computation versus quantum computation, all that. I'm having a big argument with the dean there because he's from the other. He's Bill, you're nuts. That's never going to work. So okay. As long as somebody thinks it's going to work, we can sell them measurement equipment.
All right. I promise not to descend on anybody, and we let people who really want to ask questions. Yeah. Please, go ahead.
I'm a grad student in mechanical engineering. So since this transformation of biology has happened so quickly, what do you think the next big transformation for Agilent, the next huge market that you'll be targeting after life sciences has run its course?
In my personal belief, it's going to be in the whole synthetic biology side. And that's why we have a deep relationship here in Berkeley and with Harvard and the Wyss Institute. From my viewpoint, and again, things could change over time, but I believe the whole advent of synthetic biology will affect every one of our end parts. And we joke about, the computation side, which, quite frankly, is going to be decades and decades away. But I think that is going to have, dramatic impact on how people are going to be able to design things and conduct business.
We have one. Okay. And just one more after this, I think.
Hey, I'm a grad student in bioengineering. So we were wondering if there's ways you've thought of to improve industry-academia collaboration. So not just within one place or the other place, but and not just seminars, like a way to actually get better research collaborations, brainstorming, things where we don't worry about IP or something like that anymore, where it's really just an exchange of ideas and access to resources as we go forward.
Yeah, it's a great point, and I'll put my plug in. It's always a two-way street, and you just said the magic words, IP. But what we do is, first of all, what we've done differently, we have a central research lab. So Darlene Sullivan is our chief technology officer, has a bunch of resources as money. So we basically give away through grants or research grants moving forward, let's say roughly $6 million a year. So we have a pile of money, plus she has a bunch of researchers that she can collaborate. So that's issue number one. You want to do it from a business standpoint. The second question is who do you work with? And this is why it's so important on the flip side. You're betting on people. So we, quite frankly, go in and evaluate the schools, the professors, and the principal investigators. We do all the research on the papers. And are they going to stick around, number one? Are they going to be able to attract students? And are they going to be somebody that we can make a commitment? Because quite frankly, we still do it. We have lots of $50,000, $100,000 grants to deal with a certain project. And if you had one, you could apply. And all that's great. But in terms of long-term collaboration, it doesn't do what I think that you're talking about. And so we do that. We call it a thought leader program. To give you somehow an idea, and I give Darlene and the team a thing, when we started this, only 3% of Agilent's business was in academic, research, life science. Today it's 7%, and the company is $1 billion bigger. I mean, that's how big it has gone. And so because of the long-term commitments, and again, you know how the poor dean came up and all the questions, and I got to meet here, the chancellor here, okay, really, what is Berkeley going to do to manage through the financial mess in Sacramento and all the rest? Because it's a long-term bet on that. Once that happens, then you get to the IP. What has been so good, I think, here is that getting better master agreements moving forward and getting that stuff out of the way so that you can allow the people who do the real work to collaborate, as you described. And I think we've made great strides on, with this institution to be able to make it happen. So that's how we're approaching it. But it has to be an absolute dedicated view from a company such as ourselves to make it work. And it has to be, in my opinion, for the long haul and not just a shorter IP and you argue about, who gets the royalties.
If I can just sort of join Bill in saying this. So Bill and Darlene actually have been the founding corporate members with the Agilent. Agilent has been the founding corporate member of the Synthetic Biology Institute here, and they've actually worked through a lot of these issues. And the co-directors are right here, Adam and Doug. And a lot of the research is actually really from Agilent sponsorship of the work. So, by the way, just so that we can get as we bring this part of the program to a close, I'd like to thank you, Bill, for spending this fascinating afternoon with us.
Thank you.
On behalf of the college, I'd like to present you with a small remembrance of today's event. And here's our friends in Eta Kappa Nu. It recognizes our deep appreciation for your commitment to the College of Engineering as the 2013... I'm going to shake your hand, too.
All right. Got a picture. There we go. Got a picture? Got it?
Was that not long enough? We hold the pose here.
All right. Thank you.
It recognizes our deep appreciation for your commitment to the College of Engineering as the 2013 Koo Distinguished Lecturer. Many thanks to you. Thank you also to Eta Kappa Nu, our student co-sponsors, and most especially to Ernie and Bettine Koo for providing this wonderful forum.
Thank you so much.
That isn't the end of the program. I hope all of you will join us for the reception right outside in the Kwame Atrium. Thank you all for being with us today, and go Bears.
Yeah, go Bears.
Thank you.
Good. Thank you.
Thank you.